In this video, we're going to look at some practice problems dealing with the process of optimization for both closed and bounded domains and ones where we don't have that quality. So first, let's look at finding the global extrema, that is the global min and global max, of f of x equals x minus natural log over 0.1 less than or equal to x less than or equal to e, which is a equivalent way of saying on the interval 0.1 to e. And this is closed and bounded, which is good. However, we need to think about, is this continuous? And this is not continuous at x equals 0 because of the natural log. So because of that, we need this to be continuous, but note, 0 is not in the domain. Zero point 0.1 to e, so there's no issues, right? This is continuous on the domain, which is all we care about in this problem. So that means that we're going to do our first kind of problem. We have our closed and bounded domain. We have our continuous function over that domain. So our first thing is going to be to find the critical points. That is, find the derivative of the function, which is going to be 1 minus 1 over x. And we're going to set that equal to 0. So to do this, maybe we'll multiply by the denominator there, and we'll get x minus 1 equals 0, or x equals 1. And there is a critical point. We also need to think about when the derivative does not exist. We have at x equals 0, but note that's not the domain. So you don't have to worry about that. And at endpoints, so at x equals 0.1 and e. So we have 3 critical points to look at, which means that I'm now going to compare those 3 critical points. I'm going to look at f of 0.1, f of 1, and f of e. Now I'm going to look at all 3 of those and compare the function values. So f of 0.1 is going to be 0.1 minus natural log of 0.1, which is going to come out to be, it's to be about 2.4. F of 1 is going to be 1 minus natural log of 1, which is 1 minus 0. That's 1. And f of e is going to be e minus natural log of e, which is 2.71828 minus 1. It's going to be about 1.1828 or so. So this means that we have our global max at 0.1. And our, global min at 1. Smallest function value, biggest function value. Now let's see if this works with the graph on the next page, see if it actually works out. We have at 0.1 the global max. At 1 here, we have the min. And at e, well, this is just going to be a local maximum here, not a global max. All right, next problem. Find the global min and the global max of a function 1 over x minus 7 squared plus 2. Note that since there's no domain given, we are thinking about negative infinity to infinity. So we cannot have a closed and bounded domain. Therefore, we need to think about all the other things in this problem. Let's start with finding the derivative. To find this derivative, I think it might be best to use the quotient rule. So we'll do the derivative of the top, which is just going to be 0, times the bottom, x minus 7 squared plus 2, minus the top, 1, times the derivative of the bottom, x minus 7 squared plus 2, all over the derivative, or sorry, the bottom squared. So this is going to give us 0 for all of this. This is 0 times that. It's going to give us the derivative of the top, derivative of the bottom, negative that, which is going to be 2 times x minus 7 plus 0. Using a little bit of chain rule there, bringing the 2 out in front, then multiplying by the derivative of x minus 7. All over the x minus 7 squared plus 2 quantity squared. And I'm going to set this equal to 0, which means that I'm going to get rid of the denominator because I'm just going to multiply by the denominator on both sides. We get negative 2 times x minus 7 equals 0. Divide by the negative 2. X minus 7 equals 0. X equals 7 is our critical point. Let's also think about when the derivative does not exist. This is going to be nowhere because x minus 7 squared plus 2 is always positive. There's going to be no 0 in the denominator. So we only have one critical point to look at. And in this case, there's not really a whole lot to do. We need to just test maybe whether that critical point is a max or min, but really we could just kind of plug it in. I think it might be nice to just maybe do the first derivative test here so we don't have to find a second derivative. Look at 7, maybe we'll plug in a 0. That's always nice to kind of plug in. And maybe 8 into the derivative. So if they'll do f of 0, f prime of 0, sorry, is going to be negative 2 times negative 7 over negative 7 squared plus 2 squared. All we really care about is the sign, which is going to be positive. And at 8, we're going to have negative 2 times 1 over 8 squared plus 2, quantity squared. And again, all I care about is the sign, which is negative. So this means that we have a local max at x equals 7. Lastly, we should probably check the limits to make sure that we're not going to blow up to negative or positive infinity on both sides or one of the sides. So let's look at the limit as x goes to infinity of 1 over x minus 7 squared plus 2. And this is going to make the bottom get really, really big. It's going to be like 1 over infinity, which is going to be 0. And the same thing's going to happen for negative infinity as well. So this is going to be an increasing function before 7, decreasing after, and we're going to have our limits both be 0. That's going to tell us that our function is going to look something like this. 7 being the point that we have a max. And this means that we're going to have a global max at x equals 7. And the global max is going to be f of 7, which is 1/2. And there is going to be no global min. The reason for that is because we're going to keep on getting closer and closer to 0, but never actually get there. That's because the limit's going to go to 0. We have a horizontal asymptote at y equals 0. When we look at the graph of the function, we can see this play out. We have a little hump here at 7. That's our global max. But there is no global min because I'm just going to keep on getting closer and closer to 0. I'm never actually going to get to 0. It's a horizontal asymptote, but I can get as close as I want to that point. All right, let's do another practice problem. Consider the surge function, f of t equals t e to the negative 5t, which gives the quantity of a drug in the body at time t. Find the global extrema of f. So in this problem, note that this function has a domain negative infinity to infinity. However, but in the problem, t is time, which means that it has to be positive. So t is going to be greater than or equal to 0 in this problem. And that is our domain, 0 to infinity. It doesn't make sense to have negative time, so it's going to be always non-negative. So that's our domain. It's still not closed and bounded. It's closed on the left, but it's not bounded. So therefore, we can't use our special to plug in the critical points. But let's start with finding the critical points of the function. To find the derivative, we're going to need to use the product rule. This is going to be the derivative of t times e to the negative 5t plus t times the derivative of e to the negative 5t. This is going to give us 1 times e to the negative 5t plus t. You've got to use the chain rule here. And that's going to give us a negative 5, or I should say e to the negative 5t times the derivative of negative 5t, which is the negative 5 I was saying. This is going to give us e to the negative 5t minus 5t e to the negative 5t. There's our derivative, and we're going to set that derivative equal to 0. So to do that, I can take out an e to the negative 5t from both terms, and I'm left with 1 minus 5t equal to 0. It's important to note that exponential functions are always positive. So that part of this is never going to be 0, so we don't need to consider it. It's like a positive number. If it was a 2, we would just divide by 2 and it'd be good to go. To find the 1 minus 5t, we set that equal to 0. That's 1 equals 5t. That's going to be t equals 1/5. And there is our critical point from setting the derivative equal to 0. Think about when the derivative does not exist, and we don't have anything except for our endpoint t equals 0. So we have two critical points to consider, two things to kind of look at in this problem. Let's think about the first derivative and what's kind of going on here. The reason why we're using the first derivative test is because it kind of gives us a good idea of the shape of the graph. It's kind of doing more than just the first derivative test. Let's look at 0 here and 1/5. No, I don't care about what happens before 0. It's not part of our domain. So I'm only looking at two intervals here. Something in between 0 and 1/5. Let's look at 1/10. And something greater, how about 1? Think about what is f prime of 1/10. It's going to be e to the negative 5 1/10 times 1 minus 5 times 1/10. All I care about is the sign. This is a positive number. This is going to be a positive number, like 1 minus 1/2. This whole thing is going to be positive at 1/10. Plug in 1, and you're going to have a negative number. Because you're going to have a positive thing times a negative thing, which is negative. So this is kind of saying that the 1/5 is a local max. And 0, it's going to be increasing before 0, so this is actually going to be a local min for our function. If we plug in 0 into our function, we get 0. When we plug in 1/5, we get 1/5 e to the negative 5 times 1/5, which is e to the negative 1, which is going to be 1 over 5e. Now we need to think about the limit. There's only one limit to kind of consider. That is the limit as we go to infinity of t e to the negative 5t. The e to the 5t and negative, we can write this if you want as limit as t goes to infinity t over e to the 5t, and that makes it a little more clear that we have this dominating function on the bottom, e to the 5t. This is going to go to 0 because e to the 5t dominates. It gets bigger much faster than the t. So we can think about what the general shape of the graph is going to be at this point. It's going to be a local min at 0, local max, and then approach 0 on the right. Which means that we are going to have a global min. We are going to have a global max. Let's verify that with the graph on the next page. If t e to the negative 5t here, we actually have the point 0 there, so that's going to be our global min of 0 at x equals 0. We have our global max of 1 over, 1 over 5e at x equals 1/5. And then we approach 0 on the right, but since we actually have the function value at 0, then we do have a global min. In the next section, we're going to be looking at problems that deal with applications of this optimization idea. We're going to get even more practice dealing with these concepts. It's just going to be inside of some more difficult problems.